Welcome to our first lesson on proof. We start this year with a discussion about what proof is and what it means mathematically. And I'm going to keep it very simple at the start. I could introduce something about inequalities. If A is less than B, then we know that AC is less than BC. And this is going to be true if and only if C is greater than 0. Now, I want to kind of introduce the terminology here a little bit too. We have a biconditional here by using the if and only if. A single condition would mean going forward, if A is less than B and AC is less than BC, this means that C is greater than 0. And I know if C is greater than 0, the reverse would be true. So that's what makes this a kind of a biconditional statement. I also introduced this because this sort of inequality here and this sort of condition here about C being positive, implying that we have this product that's less than that holds. It's something we're going to be able to use a little bit later. So I got to get my speaking tone back into me. This is the start of the school year. So we have this proposition. You'll find this in the text that we gave you. That's where I'm getting a lot of this from. But we know that if A and B are both positive and A is less than B, and this compound inequality is a way to say that. This is basically saying that A and B are both positive. And you can sort of create a note to you about that. Also new tablets, so I'm trying to get used to the pressure sensitivity and some of that, so forgive some of the bad writing. But this is saying if A and B are both positive and they're both greater than 0 and A is less than B, then we know that A squared is less than AB, which is less than B squared. We also know that 0 is less than the square root of A, which is less than the square root of B. So one of the things that you want to do is you want to ask yourself, well, how do we know this? And what does this mean? Like, why is this valuable information? Or just at least convince yourself that you know what this is talking about. That's one of the things in proof you have to do a lot. Going back to the initial condition, right here, we're saying that B is greater than A. And going over here, we're saying that B squared is greater than A squared. And there's another thing, we're saying it's greater, that the product of the two is actually in the middle of them. And then we have the second condition that says that if B is greater than A, then the square root of B is greater than the square root of A. Now, both of those should kind of be a little bit intuitive. Now that you really start thinking about it, you're like, all right, I could buy that. Well, our proof uses the condition from way up here. Our proof is to take the initial A is less than B, and just to simply multiply the left side and the right side by A. I'm going to actually stick a kind of classic Algebra 1 style. Sorry, I'm teaching Algebra 1 right now, so I'm going to do this a lot. And I get A squared is less than AB. And then I could do the same thing without loss of generality, and over here multiply both by B. And I get AB is less than B squared. And clearly you can see how those piece together to show that A squared is less than AB, which is less than B squared. Now, for the second part of this, let's switch colors here. So we proved the first part, we want to actually prove the second part. For the second part, I can't believe I just switched colors again, sorry. We're going to say, assume the opposite, and I'm going to put that in kind of parentheses or quotes here because it's not really an opposite, but I don't want to use terms here too much. But assume the opposite of the square root of A is less than the square root of B. Assume the other thing. In certain cases like this, either something is true or the other thing is true. We're going to say the other thing is true. So the opposite of A square root of A less than the square root of B is the reverse of that. Assume that the square root of B is less than or equal to the square root of A. That reverses the roles completely and puts an inequality on it. Puts a less than or equal to as well. So what we're going to show is that that can't possibly be true, which means that this has to be true. And this is a type of proof, and I know this is going to be a little struggling at first, but I just kind of want to go with this. We're going to assume that this is true. We're going to start with that. This is an acceptable means of proof. We're going to start with the opposite of this thing. Now, by the original proof, meaning the thing over here on the left, we know that B is less than or equal to a. Pretty much by the original truth or proof. How do I know that? Well, because if this is true, then this must be true, because over here on the left side, we just showed that. We showed that the squares hold the same relationship as the numbers themselves. So, by the original proof, that has to be true. B has to be less than or equal to A. But this thing, which violates, trying to keep my language correct, by the original proof, B is less than or equal to A, which violates the original condition. And that original condition is this thing here, that A is less than B. Therefore, we can safely say that the square root of A is less than the square root of B. And a little symbol we can use here, once we realize that, is this little arrow inside an upside-down triangle, which means that a contradiction was attained. So I want to just kind of review this, because this is our first proof. It's a basic one. I know it doesn't seem that way, but this is actually one of the more basic ones we can do. We're starting with A is less than B, and this condition about greater than 0 is just a qualifier. It's an important qualifier, but it doesn't really speak to the truth of what's going on. Basically, we're saying if A is less than B, then the squares hold the same relationship, and AB being in the middle is just kind of a sidebar. But really we're saying if A is less than B, then A squared is less than B squared. We proved that right here. Not a hard proof to do, given the condition we started with. But the one with the square roots is just a little bit more challenging. So what we do is we say, assume the opposite. Assume that the square root of B is less than or equal to the square root of A. We show that this can't possibly be true, because by using this proof we did before, that would mean that B is less than or equal to A, which is impossible, because it violates the original condition. That's a contradiction. Therefore, the other thing has to be true. Square root of A is less than the square root of B. This is called a proof by contradiction. And it's a type of proof, one of many that we're going to study in this thing. I want to show you another proof of contradiction. This is a classic one, and this is one that I've done with some of the runners at various points on runs. Sorry, still trying to put a colon in here. And the one that we start with is, there are infinitely many primes. You know that that's true. You should kind of feel that that is true. There are infinitely many primes. But the proof is a neatly elegant proof by contradiction. So we start with this thing. We say that if there are infinitely many primes, then we're going to start with the opposite. Assume there are finitely many primes. Assume that there's a finite number of primes. And we're going to actually label those primes. x1, x2, x3, all the ways to some xn. Step 2. We're going to multiply those primes together. x1 times x2 times x3 all the way to xn, and we're going to call that product m. Now, we are going to examine m plus 1. Okay, a couple years ago I did this, and I was convinced when I saw this that m plus 1 was just a new prime. I was wholly convinced of that. Basically, if I take all the primes before a certain point and multiply them together and then add 1, I've generated a new prime. I've generated a number that is no longer divisible by x1, x2, x3, all the way to xn. But Sir Nicholas Denary, one of our first students, really had to be sold on this. So I kind of did a little side proof over here. I sort of created, if A divides B, which means that B is divisible by A, it's just another way of saying that relationship. But if A divides B, then A does not divide B plus 1. And we would just really wanted to be sold on that. So what we said is, if A divides B, then B over A is an integer. That's really what that means. It generates a clean integer. And then we say, well, let's examine B plus 1 and try to divide that by A. Well, if I do that, then I get b over a, which I know is an integer, plus 1 over a, which is definitely not an integer. This first one's an integer, the second one is not an integer. And that should prove right there that it's not divisible. I have an integer plus a non-integer, which is definitely going to give me a non-integer. So that's sort of one. You examine this in new prime, and what I can say is, since that's a new prime, that's a contradiction to my assumption that there are finitely many primes. Therefore, there are infinitely many primes. Actually, I should write that a little bit more precisely. If I want to say there are, I can say there exists, a little backwards e, there exists infinitely many primes. That's a little sloppy to do the infinity symbol in primes, but you know what I mean. And sort of the math language can get a little bit more fun than just writing all these words out all the time. So that's an example of a proof by contradiction, and I hope you could follow that, because this is a very, very useful technique in proof. One of many. Okay, let's give a definition, and we're going to use this definition in another type of proof, or another tool we're going to be using to prove stuff. And this is the definition of something you've all dealt with, absolute value. Those of you who've had Mrs. Manton, I think both of you did, we have the absolute value of x is actually defined as a piecewise function. Absolute value of x, or I can say f of x equals the absolute value of x, which equals x if x is greater than or equal to 0, and negative x if x is less than 0. And that creates it, or defines what a piecewise function is, depending on what the value of the variable input is. So a couple things follow from this. I know from this that x is always less than or equal to the absolute value of x. And that's simple enough. The left side could be negative, and the right side can't be negative. So that has to be true. It either has to be equal to, or it has to be less than. And one of the things that follows is that the product xy is going to be equal to the absolute value of x times the absolute value of y. And that should be also very obvious. And we don't say things like obvious. We say this. We say intuitive. Intuitive is one of these condescending math terms that appears a lot. Intuitive means obvious. And in math world, a lot of things are intuitive, even if they're really not. So just kind of a little heads up there. You will see that a lot. Now, a proposition is different than a definition. A proposition is something that needs to be proven. We use definitions, we use intuition, we use other things to prove things. We have different varieties of proofs. But this proposition is one that occurs quite a bit. It's called the triangle inequality. You're going to use this on the homework a bit in different kinds of proof. The triangle inequality states if x and y are both elements of the real numbers. And that's exactly what this means. X and y are both elements of the real numbers. This thing here means elements of. Or contained in. They're both real numbers. I'm going to try to start moving throughout this more towards symbols, so if you need to rewind and hear what that meant, do it. If that's true, then the absolute value of x plus y is less than the absolute value of x, or less than or equal to the absolute value of x plus the absolute value of y. Sorry, trying to get a better y there. And that's called the triangle inequality. So that's the name of the proposition. Once you prove it, you can use it, but you have to prove it in order to use it. It's one of the things about, well, you remember that from geometry. So our proof. Proofs in this are not always so straightforward. So if I give you a proof, it's nothing I'd expect you guys to get on your own, but it's one I want you guys to follow. And one of the things I had to do constantly in math in college was to try to memorize some of these. You will see these again in college in different classes that deal with proof. But having exposure to this is going to be extremely, extremely helpful. We're going to start with 2xy is less than or equal to 2 absolute value of x, absolute value of y. And I want you guys to think about why we might start there. You know, your little hint was that that's one of the conditions that we placed right up there. So sometimes that becomes a way to sort of start. And you'll see that that was not necessarily the most obvious way to start, but later on, if we work our way backwards, we could actually end up there. it's going to look like I'm cheating. Like, how would I know to do this? Don't worry, this is all wholly normal. These little feelings you might be feeling are things that everyone goes through when they talk about proof. Right now, you're just kind of looking at how it evolves, and you'll start to pick up on some of these strategies a little bit later. So we're going to add x squared plus y squared to both sides. Now, you might be able to see why that would be true, why we would do that. If I do that, I get x squared plus 2xy plus y squared is less than or equal to x squared plus 2 absolute value of x, absolute value of y, plus y squared. And we know that since a squared is equal to the absolute value of a squared, I can just do a simple replacement here and make this, I should not do that arrow, that's sloppy of me, but x squared plus 2xy plus y squared is less than or equal to the absolute value of x squared plus 2 absolute value of x, absolute value of y, plus absolute value of y squared. And then we'll do the factoring step that I know you guys can see. X plus y quantity squared is less than or equal to the absolute value of x plus the absolute value of y quantity squared. What I'm going to do is I'm going to go all the way back up to the start and kind of take a look at that. Well, with this right over here, remember, if a is less than b, then the square root of a is less than the square root of b. So how does that help? Well, if I take the square root of the left side, I get the absolute value of x plus y. And remember, the square root of a quantity squared is equal to the absolute value of that quantity. Sorry, I know that's kind of small and smudgy, but you get it. And then I have less than or equal to the absolute value of x plus the absolute value of y. And it's redundant to put absolute values there, so I'm not going to do it, because if I take a positive number and I add a positive number, I get another positive number. So that's done. One of the things we put in math, I tend to put a little square at the end, which means done. You'll also see QED, which stands for quod erat demonstratum. I'm probably misspelling that last word. But thus it is demonstrated, thus it is shown in Latin. Okay, lastly, one more proof, one more proposition. Something that you might be willing or able to use. This one's called the arithmetic or geometric mean inequality. Hopefully you remember how to calculate both arithmetic and geometric means. I expect arithmetic means, which is just a classic average, should be well ingrained in you. And geometric means is, well, it's a little bit more geometry based, but I kind of think of it as more algebra based. This is also known as the AGM Inequality, if you want to use it as an abbreviation. Obviously, just AGM Inequality for arithmetic geometric mean. So the AGM Inequality states, for two non-negative numbers, the geometric mean is at most the arithmetic mean. The geometric mean is at most the arithmetic mean. So in algebra terms, two non-negative numbers, and we'll call those a and b. The geometric mean, which is the square root of ab, is at most, which means less than or equal to, the arithmetic mean, a plus b over 2. Now, if you really want to go crazy, pause this video right now. Try to see if you can solve this one, or not solve this one, but come up with a proof of this on your own. Come up with some way to show that this always will be true, using tools that we have done. And I'll tell you right now, the only things you need to solve this are things that we have done before, and it doesn't use any techniques that you haven't done. So pause it, come back, and I'll just work step by step, and you can pause it and just get one clue and one more clue and see how far you can do on your own. Okay, I will start by saying that we're going to come back up and use one of the very first things we did. We're going to use this thing. We're going to use that in its classic sense, in its simplest sense, and just square both sides, which is really what that's saying you can do. I never called it that up there because you really should be careful about both sides within inequality. But that's the proof that says you can actually square both sides in an inequality and hold true if they're both positive. So since the square root of AB is positive, oh wait, nope, we just said two non-negative numbers. See what we did there? That should also have been a hint. And sorry about these tweets. So we're going to square both sides. I'm going to get AB is less than or equal to A plus B quantity squared over 4. So that was the first step. Again, pause it and see if you can kind of figure out what we can do there. Okay, coming back, let's just multiply both sides by a 4. So I get 4AB is less than or equal to A plus B quantity squared. And again, start to see if you can figure out why this would always be true. Give you another hint. We can square the A plus B. So I have A squared plus 2AB plus B squared. You might be able to see it now if you kind of subtract and say A squared minus 2AB plus B squared, or 0 is less than or equal to A minus B squared. And we're done. Now how are we done? Because we have hit something that is always true. And that was the goal of this. If we want to hit something that was always true or that intuitively has to be true, or when I say always true, how about this? We're going to say it's intuitively true now. This right here was not intuitively true, but we changed it using simple techniques that we've already done, nothing more than just one rule and then some algebra, into something that's intuitively true. And that's a proof technique as well. If you can take something that's not intuitively true and transfer it to something that's intuitively true, then you succeeded. Put a little QED or put a little square and you're done. Okay, that's it. Your first homework set is going to be numbers 2 through 5. This will be on the calendar 7, 18, 19, 20, 21, 24, and 28. Circle those in your packet, and that's homework set number 1. See ya.